Welcome back to your second lecture, Contemporary Math. So this is from Chapter 1B. Today we're going to talk about propositions and truth values. So the first thing that we're going to talk about is a proposition. So proposition makes a claim. Either it's an assertion or a denial. So they're saying it's a claim that's either true or there it is. Sorry. It is either true or false. I guess I should read the whole sentence. So a proposition is something that's either true or false. I could say something like, the sky is blue, the grass is green. Or I could say, the sky is green. That's a proposition as well. It's a false proposition. Something that may not be a proposition. So maybe if you're making a commanding statement, like pick up the stapler, that's not something that can be verified true or false. So maybe something like that would not be a proposition. But quite a few of the statements that we make within our life are propositions, right? We can verify them as either true or false. And so if we have a statement like the sky is blue, if we want a negation or the opposite statement, and so we want to be able to talk about whether things are true or false, and a little bit abbreviation, or when we talk about truth values, we talk about things, the quality of either being true or false. And so a lot of times we'll just write T or F to represent the truth value. And so if we want to do a truth table, we're going to let entire statements be a variable. So if we wanted, the sky is blue, right? We could let that entire thing be a statement. So it's either true. So either the sky is blue is true, or it's not true that the sky is blue. And so we want to talk about negations. If we negate the statement, if it's true that the sky is blue, then it is not true that the sky is not blue. Okay, so man, this is a weird way to introduce it. But if the original statement is true, so the sky is blue, then the sky is not blue is a false statement. And if it's true that the sky is not blue, or if it's false that the sky is blue, then it's true that the sky is not blue. So if this one's true, then this one's false. If this one is false, then this one is true. This would be P, this would be the not P. I think sometimes they do like a little not P. That's another symbol they use. I think maybe like a tilde P. There's a few different symbols that people may use for negations. Okay. So example 1 says, find the negation of the proposition Tom is the tallest student in the class. So first thing we want to do is find the negation of Tom is the tallest student in the class. If the negation is false, so we're assuming this is false, then is Tom really the tallest student in the class? So this one you might have to think about for a second. But they're saying this is false. So Tom is not the tallest student in the class. So it is not the case that Tom is not the tallest student of the class. And this is that sort of like double negation sort of thing happening. And so if it's not the case that he is not the tallest student, then it is the case that he is the tallest student. So yes, he is the tallest. Okay, and now, because you have an annoying math professor, here we go. You ask your professor if homework is due and they respond, it's not the case that there's no homework due. should you submit your work? And this is that sort of double thing, negative thing happening again. Not the case there is no homework, then it is the case that there is homework. So yes, submit your work, always submit your work on time. Okay, so going through this, if P is true, not P would be false. And if P is false, not P would be true. Now we do a not. It's a not joke, sorry. So true, false, and if we do not this is also going to be back to true. So if we do a double negation, it's the same thing as the original statement. So every time, and I think this is the way maybe to think about it, like every time we add a not, we're going to change this value, right? If I added 3 knots, I'd be back to here. So I could do crazy long things with lots and lots of knots, right? Okay, so now we want to talk about logical connectors. So there are 3 connectors we're going to talk about. We're going to talk about and statements, or statements, and if then. So now we're going to have multiple statements or multiple propositions, and we're going to connect them with like an and statement or an or statement or an if then. So we use this language within our life like every day. And so let's start with an and. And so if we think about this, there are 2 propositions. Think about how to fill this thing out. So there are a few different it can be true. It could be the case that the sky is blue. It could be this case that the sky is green or the grass is green. It could be the sky is false. So we want to think of every possible true and false combination to fill this P and Q out with. And so the best way with 2 variables is, this is the sort of way I go about it. True, 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 false. And then and now we come back to the question. P and Q would be blue. Okay, so if it's true that the sky is blue and it's true that the grass is green, what can we say about the sky is blue and the grass is green? Is that true or is that false? So we look at this statement. If we think about the case where the sky is blue but the grass is not green, is it true that the sky is blue and the grass is green? So when we say this statement, what we actually mean when we make an and statement is that this one is true and that this one is true. So if this one is false, the grass is not green, then we cannot make the statement that both of these things, right? So when the grass is not green, it's not true. It's not true that the sky is blue and the grass is green. So when the sky is blue is not true, when it is false. So the sky is not blue. Can we make this statement? If it's both of these are false, the and statement is definitely false. And so if we're looking at this, An and statement is true only when both of these things are true. And so this is sort of within the language that we use. If I'm saying I want this, and I want this, and I want this, I'm being very demanding. I want everything within what I'm saying to be true, for it to be true. So let's look at these next ones. So example 3 gives us a few more statements, a few more propositions to look at. So Austin is the capital of Texas, and Canada is a country in North America. So we're looking at two different things here. So Austin's the capital of Texas. That's one statement, and it's connected to another statement right here. And so we're looking at each of these separately. So if we're looking at Austin as the capital of Texas, that is a true statement. And Canada is a country in North America. So overall, I want to know if this thing is true or false. The and statement, overall, it is true that Austin is the capital of Texas, and it is true that Canada is a country in North America. So overall, this entire statement is true. Okay, so that's that part. The next one is the capital of Texas is Austin. And Egypt is a country. This is true. The capital of Texas is Austin. In Africa. So, overall, what can we say about this and statement? So if it's true that the capital of Texas is Austin, but it's not true that Egypt is a country in Europe, then overall, this is false. Okay. And now we want to talk about triple conjunction. So now we want to talk about throwing in two ands between three statements. So now we're connecting three statements. So we still have to think about how can we fill out throughs and the way I usually start, and I think this is kind of more, I think it's convention. There are a few different ways you can do it. This is the way I'd sort of make the pattern. So you start out with three truths. And so I kind of let this false dance to the other side. Okay. You can have true, false, false. And now I kind of let this first one dance. So you can have. And that guy can move. And also, this guy can move. So okay. So a little bit behind this. And this goes back to like a sort of simple counting principle, right? So if we have propositions P and Q, P can be either true or false. So if we think there are two options, and Q can be either true or false, and R can be either true or false. So if we're thinking about just two propositions, 2 times 2 would give us what, 4? If we're thinking about all three of them, we're going to have 8 options. So every time we add another proposition, we're going to have to multiply by 2. So if we had 4 propositions, we would have a total of 16 different options of true and false qualities, right? So these things, they're growing exponentially, they're doubling each time. So definitely, we're probably not going to try to do over 4. And if in the book anywhere they try to make you do more than 4, you can yell at me or something. I don't know. That's kind of crazy doing anything more than 4, to be honest. Because 4 of them already gives you 16, right? You're going to write off 16 different patterns. Okay, so let's get back to this. P, Q, and R. So if they are all true, and I want you to think just for a minute how to fill this thing out. You could come up with 3 different statements if you really want to. The sky is blue, the grass is green, and the carpet inside my apartment is brown. I don't know. So there's 3 statements, and if they all turn out to be true, the and statement is going to be true. If one of them is false, guess what? Whole statement. If 2 of them are false, guess what? This whole statement. All of this thing is false. So the only way that it's true, and this is going back to how we kind of did the 2 propositions, right? It's only true if everything in there is true. So and is really, really strict. If I'm saying I want this, and I want this, and I want this, it's like I'm really demanding. And is really strict. The next thing we're going to talk about, the next connector, is this or. So or is not really quite as picky as an and statement. If I say I want this or I want that, it's not quite as picky. But there is a really kind of there is a distinction we probably need to make. So there is something called an inclusive and an exclusive or. And so if we do the inclusive or, we want either or both of them. If we want the exclusive, we want one or the other, but we don't want both. So exclusive excludes the case that they're both true. Now, probably want to give you an example. Inclusive, a good example, maybe inclusive. So when you got into this test, I don't know if this is still the requirement, it might have changed. You must score a 350 on your TSI placement test, or you must have passed their prerequisite. Okay, so you either scored a 350 on your TSI, or you did a prerequisite class. So if you scored a 350 on your TSI, is it safe for you to be in here? Yes. If you passed the prerequisite class, is it safe for you to be in here? Yes. If you did both of these, if you scored a 350 on your TSI and you passed a prerequisite class, is it okay for you to be in this class? Absolutely. You went above and beyond. So both of them, you can do both of these, and it's okay in this scenario. So this one might be a little bit to the point, but exclusive is one or the other, but not both. And so one example that I give is like if you're being mugged, the person's probably going to give a demand, right? Give me $100. Right? No trigger warning on the violence, I guess. But give me $100 or I'll stab. If you give them $100, would this statement be true? Absolutely. If they stab you, would this statement be true? Yes, they held to their end on that one. Not what you want them to do, but they held theirs to their end. They weren't a liar. They might be like violent criminal, but they're not a liar, right? We can give them that. The other thing, if they do both of these, if you give them $100 and they stabbed you, guess what? Not only are they a criminal, you can call them a liar. You can call them a liar to their face, because, I mean, what else are they going to do at that point, right? So, this is the exclusive. We want one or the other, but not both, right? And really, another way to know if it's exclusive, if you can put either. Exclusive is really known as the either or. So either give me $100 or I'll stab you. If I put either in front of here, it'd be kind of a weird thing. Either score 350 on TSI or prereq. What, I can't do both of them? No, you can do both. So it makes a little more sense to put either in front of the exclusives. So going back to this, inclusive, if this one is true and this one is true, the overall, it's true. This is a true statement, right? So if you have to score 350 on your TSI or pass a prerequisite class, if you did both of them, we will include it in the inclusive or. If you just scored a 350 on your TSI, this statement remains true. If you just passed a prerequisite, this statement remains true. If you didn't do either one of those, if you did not score 350 on your TSI or pass a prerequisite class, did you score 350 on your TSI or pass a prereq? No, you did not. You did one or the other. And so this is kind of the other end of the and statement, right? Okay. So this is only false when both of them are false, right? If one of them is true, overall, this thing is true. And in general, and it says it down here, in logic, we typically assume it's an inclusive. Unless we're told otherwise, we typically assume it's okay for them both to be true. So this one looks very similar, except it's exclusive. So we don't want the case where both of these things are true. So if this is true and this is true, overall, this has to be false. Anywhere else, it's exactly the same and exactly the same kind of rationale or logic behind it, right? If one of them is true, it's true that one or the other, right? Back to the mugger example, right? If you don't give him $100 and he doesn't stab you, he was lying about that, right? And so overall, if I'm talking about ordinary language, in ordinary language, when we use the word or, that looks like, yeah, okay, never mind. That is the right word. Sorry. When we use the word or in ordinary language, you really have to look at the context. And you have to look at like what people are talking about, right? Are we talking about like some sort of standard to get into the class? Well, if you pass one of them, it's good enough, right? Or are we talking about an either or statement? And so in ordinary language, it's all determined by sort of context, right? And this is going back to the thing, like we are not logical people. We don't always do the most logical thing. And our language isn't the most logical, right? Sometimes we make sort of distinctions based on context. So we typically assume inclusive. This is the one we'll typically do. If I don't say it, it'll be this one. Example 5. Now we're going to talk about inclusive, exclusive a little bit. Kevin's insurance policy states that his house is insured for earthquakes, fire, or robbery. After an earthquake leveled most of his house, the rest was incinerated in a fire, and the remaining valuables were stolen in the aftermath. Would Kevin prefer the or? So when they say the or, to be inclusive or exclusive. So would he want it to include all of those things happening? Or would he want it to exclude the case where all those things happening? So if I say it like that, I'm hoping you're definitely getting definitely include once, right? all those things are happening to them all at once. Sounds like average typical 2020, but it would be definitely inclusive there, right? Okay, so the next one, consider statement, Austin has a public transportation system, or my dog can speak perfectly English. Is it true? So this is where things get a little funny. Transportation system, that part of it, or my dog can speak perfect English. If so, probably get some therapy of some sort. I'm trying to remember which one that was. I think it was the Night Stalker whose dog talked to him. But anyway, that's a bit of a tangent. So consider the statement, Austin has a public transportation system, or my dog can speak perfectly English. Is it true? So the dog part is obviously false, but this part is true. So if we're talking about an or statement, how many things have to be true for this or statement to be true? One of them has to be true. So overall, this or statement is a true statement. And it's a true statement because this meets the criteria right here. So as soon as we see this thing is true, we can ignore this part. That part's not true, right? But overall, this is a true statement. Okay, we're getting close. We have an if-then statement. And so we have an if-then statements. These are also known as conditionals. If P, then Q. P is considered the hypothesis or antecedent. Q is the conclusion or consequent. So maybe you just give a statement. So a good one is if I flip the switch, then the light comes on. So maybe think about that. If I flip the switch, then the light comes on. So if I broke that down, the P would be flip the switch. Q would be the light on, right? So if I think about how to do this truth table, this is my if P then Q statement. This is my P, this is my Q. So I flip the switch is true. The light comes on is true. So if I flip the switch, then the light comes on. Overall, this thing would have to be true. So it was true I flipped the switch. It was true the light came on. Then it's true if I flip the switch, then the light came on, right? The next thing says that I flipped the switch, but it's not true the light came on. So if I flip the switch and the light doesn't come on, is it true that if I flip the switch, then the light comes on? This would be the example where this thing is false. So we can determine it's false here. Because when I flipped the switch, the light didn't come on, right? Okay. So now we get to these two. So these two, and I want to kind of look at them all the same. They both have P being false. So I look at this and I make this statement. If I flip the switch, then the light comes on. So in order for this to be true, we're assuming the switch operates the light, right? So if I don't flip the switch, but the light comes on, can I say anything about the switch operating the light? So this creates a bit of a sort of something you might have to think a minute about, right? Because I haven't met my antecedent. So what can I really say about this statement if I haven't met my antecedent? So I haven't flipped the switch, so what can I say about the switch operating the light? Can I make any sort of determination about this being true or false? I can't really determine like what's happening with that, right? And so this is sort of one of those things you might have to kind of swallow a little bit. But these are known as true, and there is a sort of word we use. These are called vacuously true, right? And they're vacuously true because we haven't met this. And so if I don't flip the switch, but for some reason the light comes on, maybe there's another switch that also operates it. Who knows? Maybe there's a remote in there as well. It could still be the case that the switch operates the light, right? Just because it came on, or even if it didn't come on, right? If I didn't flip the switch, it could still be the case that the switch operates the light. I haven't determined that this thing is false, right? This is still a true statement, but it's only vacuously true, right? So that, it's a little weird. And it's a little weird because we haven't met the condition under what we're trying to base things off of, right? I think I have another example a little bit further. No, I think it's in, yeah. I think it might be, oh, there it is. Maybe if I'm elected to office, I'll reduce taxes. Right? This might be a better example, actually, maybe. Who knows? If I'm elected to office, I'll reduce taxes. So some politician is making this claim, right? He doesn't get elected to office, or she doesn't get elected to office. They don't get elected to office. Would this claim still be true? And this is sort of the vacuously true part, right? You're kind of giving them the benefit of the doubt that that thing would still be true. And so if this is something you have to swallow, this is one of those things that, yeah, okay, I can understand why you might have a little difficulty swallowing this thing, right? It's not directly obvious why this thing should be true. And there are, to be honest, there are reasons beyond this, right? And I'll talk about it towards the end. There are more reasons why we choose the way we choose things conventionally, right? There's reasons why we choose the inclusive or. There's reasons why we allow these things to be true. Evaluate the truth of the statement. If 1 + 1 = 3, then 2 + 9 = 5. And so this is what I would do. I would look at these statements. This one is false. But we know overall the if-then statement, if the first thing is false and the second thing is false, this is that vacuously true thing. So this thing is vacuously true. So you're putting together two false statements, but overall it's true. And going back to that, you're assuming it's vacuously true because this first antecedent is not met, right? If I say if something and it's something that can never be true, that overall we just kind of just generally assume, like kind of if pigs can fly, right? If pigs can fly, the monkeys can come out of my butt, right? Something like that. Well, that's a true statement. Oh, there it is. Sorry. Next one. Maybe I should read ahead a little bit. If pigs can fly, then I can jump over the moon. Again, this is a false statement. This is a false statement. So overall, this is true, right? And this is that vacuously true sort of thing. So a lot of things we say are conditional, right? There is a sort of, what would I say, consequential sort of relationship between these things, right? But a lot of things we say are if-then statements, and we'll default to the if-then, and we'll probably be translating things to if-then. But there are a few different ways we can say if-then statements or conditional statements. Okay, so the next thing we're going to do is a little bit of translating, and I think we're getting close towards the end here. We got 2 more pages. Oh, the last one's barely even a page. Okay, so number 8. We want to rewrite the following statements in the form of if P, then Q. So global warming will elevate sea levels. So this sounds like the P will lead to Q. So maybe I should keep this up here, maybe a little bit. Let's do this. Maybe I can keep them all on like one sort of page then. We all see this? Okay. So global warming will elevate sea levels. So I want to do if P then Q. P will lead to Q is what this looks like. So if global warming continues, then sea levels elevate. If global warming continues, then sea levels elevate, is what that should say. Drinking water is necessary for survival. So now this is Q is necessary for P. So you might want to note that like Q is coming first here, right? So what we should actually start with is this one. If you want to survive, so if you want to survive, then the last thing we want to translate here is a leak in the gasket is sufficient to mean it should be replaced. So this looks like the P is sufficient for Q1. So if there's a leak in a gasket, then you should replace it, is what this sounds like. Okay, so I think it's important to be able to like sort of draw these things out of normal language. And just to note, like these say P, Q, P, Q, P, Q. So these first 3 phrases have P and Q in the if P then Q order. These next 3, Q is necessary for, Q if, and Q whenever. Those things reverse the order of P and Q, right? And so these things, and I even have to double check myself sometimes, because these sound very similar, right? So sometimes even I have to check myself on these. So that is something that does take a minute, and does take a minute to think about. Okay, so we have translated that from English to logic. Okay, and now going back from logic to English. So we have a conditional statement. It looks like if P then Q. So I came up with a silly example, but if you jump up and down, then you will be tired. Okay. Converse would say something like if Q then P. So we want to change those things around. So if you're tired, then you jump. So maybe like compare that to the original thing. So the first thing says if you jump up and down, you'll be tired. The next thing says if you're tired, then you jumped. And so I want you to think, does that really say the same thing? So this one says if you jump up and down, then you'll be tired. So this one, I don't know, to me, this one kind of allots other things could also make you tired. But this one is saying if you tired, then you jumped, right? This thing to me is just kind of saying the only thing that can make you tired is jumping, right? Which is kind of weird. That's what it's saying. Okay, we'll give it to it. Okay, next thing looks like the inverse. So if not P, then not Q. So if you did not jump, then you did not get tired. And the last one is if not Q, then not P. So that looks like if you did not, get tired. So if you're not tired, then you didn't jump. Okay. So I think the conditional, the easiest way to remember the sort of conditional is that it is what? It is, I got it here. There we go. Let's go back to this thing. It is false only in one place, right? And so that's kind of the place to like lay things down. So when our antecedent is true, but our consequent is false. So if it's true, then false. So if it's true and then false, this thing is false here, it would be true elsewhere. Converse is the other way around. So when Q is true but P is false, would be in this line right here. So this line right here is where our converse is false. And this is true elsewhere. The inverse, if not P, then not Q. So not P is the first thing. So when not P is true and not Q is false. So not P is true and not Q is false is where this thing should be. The contrapositive says if not Q, then not P. So where not Q is true, not Q is true here and here, but not P is false. Looks like right in here, right in this line. So right here in this line is where our contrapositive is false. I check the other things, but they should also be all true. And I know I'm kind of like maybe skimming over that a little bit, but this is what our truth table should look like if we look at those and we follow the same pattern that we used in the if-then table, right? Now I want you to look at these things just for a second. Kind of alike. And these two things look kind of alike. And so what those actually are is those are called logically equivalent propositions, right? And so two propositions are logically equivalent. If one is true implies the other is true and vice versa, right? The truth tables on the truth values on the truth table are going to be all equivalent. And so which of the following are above are logically equivalent? The conditional and the contrapositive. So let's go back and like maybe look at our example. So if you jump, then you're tired, right? So jumping makes you tired is kind of what it's saying. If you jump, then you're going to be tired. Well, if you're not tired, then what can you tell me? Or if a person's not tired, then you can tell me that they didn't jump. So these two things are logically equivalent when we say them, right? If you jump up and down a whole bunch, you're going to be tired. Well, if you're not tired, then I can guarantee you didn't do some jumping, right? Okay. This other one, on the other hand, is like if you're tired, then you jumped. Well, if you're tired, the only way you could have done that is by jumping, right? is kind of what this is implying. Well, if you didn't jump, jumping's the only thing that can make you tired, then you're not tired. So that's weird because it's not true in reality, right? But if we assume like jumping was the only thing that could make you tired, this next thing would also be true, right? And so we have these sort of things, they are logically equivalent. Do we have one more? We got one more after this, huh? But we're almost there, almost there. Okay, where am I at? Consider a statement, if a creature is an iguana, then it is a lizard. Is that true? Yes, I believe that's true, right? Write its converse, inverse, and contrapositive. Evaluate the truth of each statement. Overall, if a creature is an iguana, then it is a lizard. Overall, this is a true statement. I can guarantee that if I have an iguana, then it is going to be a lizard. The converse says if it's a lizard. So the con, and this is the way I sort of remember these sort of things, the converse, so if you have a con, there's a sort of con going on. I think of cheesy old movies with the swap. There's some sort of swap, you know, they're swapping a briefcase, they're swapping something or another. There's a swap of the P and the Q. So for con, we swap the P and the Q. So we start with the consequent. So if it's a lizard, iguana. And guess what? If this one's true, maybe not all the time, but this one, if we think if it's a lizard, are we guaranteed that it's an iguana? No, we're not, right? All the time. There might be a few, there are a few cases where they might both be true. But typically these will have differing values, right? Okay. The inverse. So the inverse is when you start inversing things. So if we think about like additive inverses, we start negating things, right? So we want to keep things in the same order. So if it's not an iguana, a lizard. I'm also writing at a weird angle, so the things come out weird sometimes. So if it's not an iguana, then it's not a lizard. Is that true? So if we think about this, if it's a lizard, then it's an iguana. That's not true because there's other lizards that are iguanas. So if it's not an iguana, then it's not a lizard. Well, that's not true. Well, let's think of a bearded dragon, right? Maybe give you a solid example. I got a bearded dragon, it's a lizard, but it's not an iguana. I got a bearded dragon, it's not an iguana, but it is a lizard. Ooh. So this is true, this is false. Overall, this would have to be false. The last thing is a contrapositive. So that is, we're doing two things. We're swapping the order and we're negating things. So if it's not a lizard, so if we don't have a lizard, so now name something that's not a lizard, then it's definitely not going to be an iguana. So this is also true. This is going back to that sort of thing. If it is an iguana, then it is a lizard. If it's not a lizard, then it's not an iguana. And so that is the last of these notes. There's one little tidbit I want to maybe leave you with. There's this thing called Boolean algebra. Boolean algebra is used quite a bit in like computer programming. And so if we go back and we use those truth tables, and we actually give like quantities to true and false, right? We let true be 1, I believe is what they do, and false is a 0. We can actually come up with like a sort of binary sort of thing happening. And we can come up with operations. And this is another reason why we like to define the way
the connectors, this is one of the reasons why we define connectors the way that we do define connectors, right? That's the same thing as multiplying like P times Q. That's like taking plus Q. There's also some overlap you have to take off in there. And so when we get to Venn diagrams, you might see this pattern happening again. But this stuff is referred to as Boolean algebra, and we can actually create quantitative operations off of this thing, right? And we can tell computers to do, what do I want to say, truth values, right? We can ask calculators or computers to calculate truth values. And that's a lot of on how computers kind of work, or a basis on it. So I will see you soon in class.